Right, next I'd like to cover the other main type of addition to alkenes, and this is where it's specifically an alkene with an electron withdrawing group on it. And we covered this chemistry a little bit in CHEM444 II, but we're going to learn a lot more about it this semester. You may recall the Michael addition is where you add something to an electron-deficient alkene and you generate a kind of enolate type intermediate. And I have a mistake here. It's okay. We actually get a simple addition like this. So we end up with a minus on here initially, and then under the reaction conditions that will pick up a proton either in workup or during the reaction to give you this final addition product. So the mechanism in fact is really to form that initially and then that could be H3O plus, something like that. So again, we're using copper. It's another soft metal like palladium, does a lot of the same chemistry. Copper 1 is particularly good for that. And again, this is the organocuprate that's hopefully getting quite familiar to you. Tolerates a wide variety of R groups. It can be sp2 or sp3. The mechanism is similar to the Michael, but whenever you have copper 1, there's a likelihood of there being radical intermediates as well, so it's probably not as simple as a Michael addition would be with something like Cn minus adding. But the net process is the same. Now, it's obviously how well this reaction goes depends a lot on the electron withdrawing group. And if you have a really strong one like nitro, it goes pretty well. So it's been observed it's fast with nitro, with aldehydes, that's supposed to be an H there. Even ketones add quite quickly to this. It's slower for some others, such as an ester group or a cyano group. Now, in cases where you have a sluggish reaction, there are some tricks for helping to drive the reaction or speed it up. Let me show you those next. So you can either add a strong Lewis acid such as BF3 at the start, and that enhances the power of the electron withdrawing group and makes the alkene more electron deficient. We use the etherate of BF3 because this is a liquid. I have a bottle of it in the lab there. BF3 itself is a gas. It's rather hard to work with. So another trick we can do is to add trimethylsilyl chloride or chlorotrimethylsilane. And what this does is it quenches the enolate that we formed, and that helps pull the reaction through. let me give you some examples. So if we take acrolein and react it with lithium dibutyl cuprate in THF, and they use HMPA. That's a highly polar aprotic solvent that we try not to use too much because it's very toxic, but now, although the aldehyde is one of the groups I said is a more reactive one, we're trying to keep the temperature down. I guess this is quite a reactive aldehyde. You can polymerize and things like that. So remember, this is just TMS chloride. We end up in effect with a TMS protected enol, and when we add H3O plus to that, that will give us now the enolate itself, here we quenched it and made it a silicon enolate, but you can also use the enolate directly for enolate chemistry, for instance with alkylation. So let me show you that next. So this enolate intermediate can be used for any of the usual enolate chemistry, for example alkylation. And this is a reaction we learned in CHEM444, just an SN2 type process. Enolate plus alkyl halide gives the alkylated ketone. So we don't need LDA and all that stuff. So this reaction is very powerful. We're putting two different R groups. The R1 comes from addition of the lithium dialkyl cuprate, as we showed before. Then the second R group comes from a different alkyl halide that we add. Now I've shown these as trans. In a ring compound like this, they would usually go on opposite sides. So this side this face of the ring is a little more crowded, so the R2 will usually tend to come in from below. Now, just as a final thought, I also want to mention that trialkyl boranes they can also add to systems like this to give something like that. But that covers most of the addition to alkenes, and so next we're going to cover alkylation of alkynes.